In this video, we'll be looking into the introduction part of dynamic programming, and we'll be dealing about the three examples specified in the textbook. So starting from the definition, dynamic programming. So it is a technique for solving problems with overlapping subproblems. So subproblems arise with a recurrence relating a solution to given problem with solutions of its smaller subproblems of same type. Yeah. So instead of solving overlapping problems, subproblems again and again, it suggests to solving each subproblem only once and recording its results in table from which solution of original problem can be obtained. So instead of solving, despite of knowing solution of a subproblem, we keep on solving it again and again. By this, there is a wastage of space and resources. In order to overcome this, we can store the solution in the table, and whenever that particular problem arises, we know its solution. For 1,4, suppose the solution is 5, it is stored here. So this solution could be retrieved and further solved. That's how dynamic programming works. So understanding the definition DP, dynamic programming is a method that can be used when the solution to a problem can be given as a result of sequence of decisions to get optimal solution. So it avoids the enumeration of some decision sequences that cannot be optimal. Thereby it saves time and space. That's what we have discussed. So an optimal sequence of decision is obtained by principle of optimality. We'll look into what principle of optimality is. So the optimal sequence of decision has the property that whenever the initial state and sequences are, the remaining decision must constitute an optimal decision sequence with regard to state resulting from the first decision. That is, if we take the Fibonacci of a number, that is n is equal to 5. For this we have Fibonacci 3 and Fibonacci 4. 1, here 1 is repeating, 1 1 0 0 1 1 1 1 0. So whenever we have 0, we can use this recurrence relation. Whenever we have 1, we can use this recurrence relation, 1 n is equal to 1. And in case of any other numbers n greater than 1, then this particular equation could be reused. So by doing this, we get the recurrence relation as t of n is equal to 2t of n minus 1 plus 1. Yeah. So solving this further, we would get as order of 2 power n. So this is what the time complexity for Fibonacci of a number. But in general, understanding the principle of optimality, the decision has the property that whenever initial state and sequences are, the remaining decision must constitute an optimal solution. Like that's what we have discussed here, right? The remaining decisions comprised of optimal solution here, which was calculated earlier. It was calculated at the first step, and then a recurrence relation was established. So from this relation, whenever these same values were encountered, it was fetched from this particular data. So this was about dynamic programming introduction part. Let's quickly look into the three examples. So here we have the first example, that is coin row problem. So for a coin row problem, there is a row of n coins whose values are some positive integers c1, c2 till cn. The goal is to pick the maximum amount of money subject to a constraint that no two coins adjacent in the initial row can be picked up. So f of n be maximum amount that can be picked up from row of n coins. We can obtain recurrence relation as for f of n as f of n is equal to maximum of c of n plus f of n minus 2, except that whatever is beside that adjacent, except that we'll find out for the other coins. Okay, so that's what n minus 2 we have taken, comma f of n minus 1. Combining these two will check, and f of n minus 1 also will check for n greater than 1, and we'll take the maximum value. If it is 0, for if f of 1 is equal to 1, then we initialize the value as 1 itself. We can compute f of n by filling the one row table from left to right manner, similar to the way it was done for nth Fibonacci number by algorithm. We have seen the algorithm, right? So looking at the algorithm here, algorithm coin row. So here C of 1 to n, C comprises of C is an array of positive integers indicating the coin value. Then we have the output, that is maximum amount of money that can be picked. So initially we are taking f of 0 as 0 and f of 1 as c of 1. F of 0 is 0 states that initialize the base case of the f array. Here f naught is set to 0 because there are no coins to pick. Initially there are no coins to pick, right? So we initialize it to 0. F of 1 is equal to C of 1 means the maximum amount of money that can be picked up from just first coin is simply the value of coin itself. That's why we are equating it as C of 1 only. Next we have for I is equal to 0 to n. For I is equal to 0 to n, that is we start iterating from the second coin. Here we are taking the index from the second coin to the last coin, that is nth coin. We are iterating it. This loop will fill the f table value. It will fill the f table value which tracks the maximum amount of money that can be collected from I number of coins. Then we have f of I is equal to max of C of I plus f of I minus 2. This is 1. Or we have f of I minus 1. So here this particular equation is used to calculate the maximum amount or the maximum money that can be picked up from I coins. Okay, so here we have two options to select. So first is pick the ith coin. So in order to pick the ith coin, we just add the current value C of I value to the best solutions 2 positions back, that is f of I minus 2, because we cannot pick the adjacent coin. No? Beside that coin we'll see. Okay, then we have f of I minus 1. So the best solution is 1 from the previous solution. It could, if the suppose if we are here and I minus 1 is here, if the previous solution has the best value, then we can pick that also, right? So among these two we are selecting the maximum value, and finally we are returning the final solution, that is final array, which comprises of the values. So let's look into an example. We'll understand this better. So here we have coin row problem. These are coins 5, 1, 2, 10, 6 and 2. So maximum amount should be picked from these coins. Firstly we'll write the index value. For 5, 1, 2, 10, 6, 2, it will start from 1 to 6. Initially we are taking f of 0 as 0. F of 0, this is the f table. F table is, finally we are returning this table, right? So this is the f table. So f of 0 is 0 and f of 1 is C of 1. The C of 1 value is 5. So f of 1 is, we are equating it to 5. We have written 5 here. Done. Next, now we'll take I is equal to 2. For I is equal to 2, maximum of C of 2. That is what we have done. F of I is equal to max of C of I. Maximum of C of 2 plus f of 0. We are adding f of 0 here. Previous value, comma. We are taking I minus 1. That is I is 2 here. So 1 will take. So maximum of C. C of 2 is 1 plus f of 0 is 0. We know this. Comma 5. F of 1 is 5. So maximum of these two will get 5. So we added 5 in the table. Next, for I is equal to 3, we take C of 3. C of 3 is 2. We added 2 here. Plus f of 1. F of 1 previous value which we had obtained from the f table, that is 5. So I added 5 here. And f of 2 here. F of 2 is 5 here. So 5 and 5 I added here. So f of 1 and f of 2. Yeah. So I get 7 here. So 7 I written in the table. Similarly, it goes for I is equal to 4, where maximum of C of 4. C of 4 is 10. So 10 I wrote here. And previous value f of 2. F of 2 was 5. So I wrote 5 here and 7 here. F of 3. F of 3 I have written it as 7. That is previous value which I have obtained here. I have written it as 7 here. If I 10 plus 15, 15 comma 7, maximum is 15. So I write 15 here. It goes the same for I is equal to 5 and I is equal to 6 as well. Now that we have filled the F table here, our next step is to find the optimal set. So in order to find the optimal set, we need to backtrack. So we need to backtrack through the F table. So firstly, I'll start from this point. Okay, F of 6 is equal to 17. So F of 6 is equal to 17 is achieved by C of 6 plus F of 4. C of 6 plus F of 4. So C of 6 is 2. So this is included here. So we keep it. Okay. Then we move to F of 4. Okay. F of 4 is equal to 15, which is achieved by C of 4 plus F of 2. So C of 4 is included here. So we keep it. It is achieved by C of 4 and F of 2. So C of 4 is there for F of 4. Then we keep this. And F of 2. What is F of 2? We'll look into F of 2 now. F of 2 is 5. So it is achieved by F of 1, not C of 2. C of 2 is not included here, but C of 1 is equal to 5 is included here. So we have to include C of 6 first, then C of 4 second, and C of 1 as C of 1 we have to include. So I have written the optimal set of coins here. C of 1, C of 4 and C of 6 would be included. And by considering these coins only, we can get the maximum amount. and we are also obeying the condition that no two coins adjacent in the initial row can be picked. So this was about coin row problem. I would suggest you to go through the algorithm and like understand this particular example. Again, it is very easy. Let's move on to the next topic we have is coin change problem, example 2. So given a change for amount n using minimum number of coins, here we are discussing about minimum number of coins of denomination d1 to dn. So for the coin denominations, there we use a dynamic programming assuming availability of unlimited quantities of coins. There are no limits for the coins for each m denominations. So d1 is less than d2, d3 and so on, where d1 is initially or taking d1 denomination 1 as 1 itself. So let f of n is be the minimum number of coins whose values add up to n. We can obtain recurrence relation as f of n is equal to minimum. We'll be calculating n minus d of j. Here n should be greater than equal to d of j plus 1, where n is greater than 0. If it is 0, then we directly take it as 0 itself. So this was about the recurrence relation. So we can compute f of n by filling one row table left to right manner, but computing a table entry may here requires finding the minimum of up to m numbers. Previously we looked into maximum amount of money. Here we'll be looking into minimum minimum number of coins which are required. Next we have is change. We'll look into the algorithm part. Algorithm change making d of 1 comma m to n. Here input is the positive integers n, array d of 1 to m. So here we are taking the positive integers initially, and along with that we are taking the denominations also. D of 1 is 1, we know that. Here we have seen d of 1 is 1, we take it. Then output is minimum number of coins that add up to n. Okay. So for initially we are taking f of 0 is equal to 0. That is, we are initializing the base case for the f table. So f of 0 is set to 0 means no coins are needed, to make amount as 0. That's why we are taking it as 0. Now I is equal to 1 to n. So we start iterating amount from 1 to n. So this loop will fill the table, f table, where each f of I represents the minimum number of coins needed to make amount I. Then we get into this. Here temp is infinity and j is 1. So initializing temp to infinity to keep track of minimum number of coins that are needed for each sub problem. That's why we are taking it infinity here. And j is equal to 1 to n. J is equal to 1. We are iterating over the denominations. Here initially denomination is 1, right? We are starting from 1. Then we look into the while loop. While j is less than equal to m and I is greater than equal to d of j, do. This states that we continue the loop as long as there are more denominations to check this condition, and the current amount should be greater or equal to the denominations d of j. So this ensures only valid denominations would be considered in this particular step. This obeyed. We'll get into the temp. We'll get into the next line. That is, temp is equal to minimum of I minus d of f of I minus d of j, comma temp. So out of these two, we are selecting the minimum one. That is, we are updating the temp value to minimum of its current value and the number of coins needed to make the amount I minus d of j. This is the amount plus one additional coin of denominations d of j. Okay. Then here temp also we are taking as among those two, we'll be selecting one minimum value. Here before updating only temp value we are taking no. Yeah. So then we have j is equal to j plus 1. That is, we increment j to consider the next denomination in the list in the given question. Then we are taking f of I is equal to temp plus 1. F of I is equal to temp plus 1 after evaluating all the denominations. When we reach the end, for current amount I, we store minimum number of coins found in f of I. So it will be stored here. This tells the optimal solution for the sub problem of making amount I. Then we are finally returning f of n, that is the value of f of n which contains minimum number of coins that are needed to make amount n. So this was about the algorithm part. I know it's slightly tricky, but then if you understand the exemplar problem, it will be easy to understand. So let's apply the algorithm to this example, which has denominations 1, 3, 4, and here the index values for 1 is 1, 3 is 2 and 4 is 3, and the amount which they have told is 6. So firstly we'll start with initializing f of 0 to 0. That's what first step we have done in the algorithm, f of 0 to 0. Next we increment the value, I is equal to 1. So denomination considered here is 1. Then we calculate f of 1 is equal to minimum of where do we have it? Minimum of f of I minus d of j comma temp. I minus d of j. D of j is 1 only, right? Comma temp. Temp is 1. So minimum of 0 plus 1, we get it as 1. This states that amount 1 can be made with one coin of denomination 1. Yeah. Next we take I is equal to 2. Then so all these values f of 1 will be updated in the f table. So 0 we are taking it as 0. For 1 we got 1. For I is equal to 2. For I is equal to 2, f of 2 is equal to minimum of 2 minus, here denomination considered is 1 only. Okay. So f of 2 is equal to minimum of 2 minus 1 plus 1. That is minimum of 1 plus 1 we are taking. That is we have got 2. That is amount 2 can be made with 2 coins of denominations of 1. So 2, we have written 2 here. Then for 3 we'll be considering 1 and 3. So here it will be, denominations would be 1 comma 3. So here it would be 3 minus 1 comma f of 3 minus 3. 3 minus 1 is 2, denomination is 2. That is 2. For f of 2 we got 2, so I have written 2 here. F of 3 minus 3 is 0, so for f of 0 I have got 0, so 2 comma 0 plus 1. So minimum of 2 or minimum of 2 0, minimum of 2 comma 0, so I got 0 plus 1 is 1. That is amount 3 can be made with one coin of denomination of 3. I hope you have understood this particular statement. Here we are considering 1 comma 3, so denomination, only one coin is sufficient to make the denomination as 3. We have written 1 here. For 4, I take 1, 3, 4. Okay. So 4 minus 1, 4 minus 3, 4 minus 4 plus 1. 4 minus 1. F of 3 is 1. F of 4 minus 1 is 3. So f of 3 is 1. F of 1 is 2. F of 0 is 0. So I have filled the values here. That is 1 I got. That is amount 4 can be made with one coin of denomination 4. Next for 5, I consider 1, 3, 5. I get 2 here. And for 5 I get 2. That means the amount 5 can be made with 2 coins. One of denomination 3 and another one of 1. 3 and 1. If I combine, I can get 5. Then for 6, amount 6 can be made with 2 coins of denominations of 3. Okay. So this was about finding the values to fill in the F table. Once I've filled the values in F table, I have to determine which coins form the optimal set, right? So that for this we have to backtrack from f of 6. So here f of 6 is 2. So I write f of 6 is 2. So this was achieved by using d of 2. Denomination d of 2 is equal to 3. So a coin of denomination 3 is included. So I can include 3. Again, now I'll consider this 3. F of 3 is equal to 1, achieved by d of 2 is equal to 3. Again, so again a coin of denomination of 3 is included. So optimal set of coins here are 3 and 3. Here 3 was included, here 3 was included, amount was 6 I wanted. So I got 3 and 3. Without looking into the algorithm, in general terms if you have to look, so amount is 6. We have to select minimum coins. I have 1 coin, 3 coin and 4 coin. Out of 1, 3, 4, which minimum, like if I select 1 coin, one number of coins I should select 6. If I select 4 plus 1 plus 1, so I get 3 coins here. But then if I select 2, 3 coins, I would get 6. So using common sense also we can deduce that coin change problem is pretty simple. They give an amount, denominations are specified, we should select minimum combinations, coin change problem. So this was about second example. Let's look into the third example now. That is, we have coin collecting problem here. So let's quickly look into the algorithm part of this. So here this algorithm applies dynamic programming to compute the largest number of coins a robot can collect on n cross m board by starting at 1 cross 1 and moving right and down from upper left to down right corner. It has to start, suppose let's take this as a box. So it has to start from this position to, it has to reach to this position. That's what they have told. Robot has to move in such a way and select largest number of coins in the process. Okay, so that's what coin collecting robot problem states. So here we are taking input, that is a matrix of whose elements are equal to 0 and 0 for cells with and without a coin respectively. So output is largest number of coins the robot can bring to the cell n comma m. So initially we can say that this algorithm aims to collect maximum number of coins that the robot can collect while traveling from top left to bottom right, okay, of the box. So we are starting from f of 1 comma 1 is equal to c of 1 comma 1. That is, we are initializing the value of starting cell. This is straightforward because the robot can collect only it can collect only the coins which are present in the starting cell. This particular cell, if whatever coins are there, it will be stored in the f table. That's what this first line refers to. Then we are taking j is equal to 2 to m. F of 1 comma j is equal to f of 1 comma j minus 1 plus c of I comma j. This means, like, for j is equal to 2 to m, we are iterating through all the columns in the first row. Yes. Then we are taking this, the second line refers that for each column in first row, compute the maximum number of coins that can be collected by moving from left to right. So the value 1 comma j here is obtained by adding the coin value of c of ij to the maximum number of coins collected from the previous cell. That is j minus 1 I am taking here. Okay, 1 comma j minus 1 in that particular same row only I am looking. Okay. Next I am taking I is equal to 2 to n, do f of I comma 1, f of I minus 1 comma 1 plus c of I minus I comma 1. So here I am iterating through all the rows of first column here. So for each cell in first column, I am computing the maximum number of coins that can be collected by moving downwards. So the value of f of I minus 1 is obtained by adding the column value, the coin value here, that is c of I comma 1, to maximum number of coins that are collected in the previous same column, that is I minus 1. Here if you look, here it is the same row, here it is same column. These two differences, I hope you have understood the difference here. Next I am taking j is equal to 2 to m. J is equal to 2 to m, do. Here one line is missing. For I is equal to 2 to n, do. For j is equal to 2 to m, do. For I comma j is equal to maximum of I minus 1 comma j, f of I comma j minus 1 plus c of I comma j. Here we are iterating through all the rows, then all the columns of second row and second column, and then we are calculating the maximum number of coins that can be collected by taking maximum value from the cell. So here we are taking the rows and columns also, and finally we are returning f of n comma m, that is return the value at bottom right corner of the grid, which represents the maximum number of coins the robot can collect from moving from this part to this part. So this was about the algorithm. Let's look into example. So consider the following example grid. So this is the example. We have the grid is present here. The robot's goal is to collect maximum number of coins by moving from top left to bottom right. It has to start from here and it has to move here. Okay. So initially we are taking f of 1 as 1 and c of 1 as 1, and we are storing it in the f table. 1 is stored. Okay. Next, first row, if I start filling the first row, that is 1 comma 2, by applying the previous in the algorithm we have seen the formula, right? 1 comma j minus 1 plus c of I comma j. 1 comma j here is first I am taking it as 2, then 3, then 4. Here I minus 1. Here if it is 1 comma 2, here it is 1, 2 and 3. And finding these values I get 1, 1, 1. And for the first column again I am applying the algorithm. So 2 comma 1, 3 comma 1, 4 comma 1, I find values 2, 2, 2. So similarly I fill rest of the table. For 2 comma 2 it is 3, 2 comma 3, 2 comma 4, 3 comma 1, 3 comma 2, 3 comma 3, 4 comma 1, 4 comma 2, 4 comma 3. 4 comma 1 need not be filled. 4 comma 2, 4 comma 3, 4 comma 4. So I continue this process for all the remaining grids. So at the end, the final table will give f of 4 comma 4, which is maximum number of coins that can be collected reaching bottom right corner. So to find the optimal path, we need to backtrack to f of n comma n. So we should start from f of 4 comma 4 and backtrack to see from which cell it could have come, either from above or from the left part based on the values. So this was about the coin collecting problem. So this approach ensures that the maximum number of coins are collected is efficiently while navigating from top left to the bottom right corner. Suppose the robot is here and it has to move here, and meanwhile it has to collect maximum number of coins. So either it can move left or it can down right. Okay, coin collecting problem is slightly trickier, but then I would suggest you to refer textbook once, go through it. It is clearly mentioned there along with proper explanation. If you have any doubts, do let me know in the comments and subscribe to my channel. Thank you.